All right, we're going to move on to the next section. It comes in a new chapter of the book called Chapter 3, where we look at exponentials and logarithms. Before we do that, we're going to look at a set of functions we call inverse functions. And we're going to ask a basic question. If you have an equation and you solve for one of the variables, what is it are we really doing? Okay, what we're doing is we're trying to create a new function that will give us the value of this new function in terms of whatever the other variable is. And sometimes we look for one variable versus the other variable, and we go back and forth. And what we're essentially doing is we're working with inverse functions. So we're asking a very basic question about what it is we've been doing so far in this course. Okay, so let's look at an example. Suppose I have this function, right? And this is a linear function. Okay. And I've solved this for x. So let's just go through and do the steps. This is what I'm after. So I'm going to basically, anything that's not x, I'm going to try to get on the one side. So let me subtract 1 from both sides. Okay, no, I can't add or subtract anything, so now I'm going to divide. So that's my next thing, is to divide and multiply. So I'm going to divide both sides by 3 to get this. So I have this relationship. Notice I've defined a new function. Okay. And if you give me the value of y, I can figure out the value for x. So I've got two different functions here. I've got this thing, and I've got this thing. Let's go back to this one. This one's a little easier to think about. So what does this say? This says that y is a linear relationship. It happens to be in slope-intercept form, so I know it goes through the point 0, 1. I know it has, oops, let me redo that, that was bad. It goes through that point. I know it has slope 3. Okay, let's label our axes. Okay. What does it say? This says, if you give me a value for x, I can figure out the corresponding value for y. Right? So this is going to be for any given value of x, I only get one value of y out. What does this other function do? This other function says now, if you give me y, I'm going to go backwards and figure out what the value for x is. Okay? So there's an intimate relationship between these two things. One is asking what is y given x, and the other is what is x given y. And we're basically looking at the same function, only going back and forth. Okay. So let's look at this another way, and let's notice something. Okay. So for these two functions, let me call this h. There's a special thing about this, is that if I compose these functions, what should I expect to get? Well, h tells me what the value of y is given x. G tells me the value of x given y. So if I compose these, if I look at h of g of y, this is the value for x associated with y, but then h tells me what the y value is associated with x. So I should get the value of y right back out of there. Likewise, if I go the other way, h tells me the value of y associated with x, but g gives me the value of x associated with y. So I'm hoping I should get that if everything goes according to plan. So let's see what happens. So let's compose h with g, see what we get. What does g say? So I got to work on the inside out. G says if you give me a number, I take that number, subtract 1, take that result, and divide by 3. What does h say? H says you give me a number, I take whatever you give me, multiply by 3. So that's the number I'm giving it. And then whatever result I get from that, I add 1. So now notice these 3's cancel. And now y minus 1 plus 1 is just equal to y. So that works out the way I was hoping it would. What is g of h of x? Again, we have to work from the inside out. So G says do something with this number. We gotta figure out what that number is to figure out what we're doing. What is H? H says, give me a number, I multiply that number by x and add 1. So that's my new number. What does G say? G says, take whatever number you give me, in this case 3x plus 1, you subtract 1 and divide by 3. So let's see, so now 3x plus 1 minus 1 is 3x. So I'm going to simplify the numerator. Now I can cancel these 3's, and I just get x. Okay, so, so now the question is, can we always do this? And the answer is no. Okay? We can only do this in certain circumstances. And for this, we're going to need something called one-to-one. Okay? So before we talk about what that definition means and why we need that restriction, let's look at an example that will help guide us when we're trying to do these things about going backwards. So from this example, let me define a function I'll call Bob. Bob says take a number, whatever number you give me, I'm going to square it. Okay. Let's look at an example. Suppose I tell you the height of the graph of Bob at a given number x is 4. So when I plug in x to Bob, I know I get out 4. What is x? Is the question. Okay, well, here's the thing. What does Bob say? Bob says, whatever number you give me, you square it. Now there's a problem. There's two solutions to that. X is equal to 2 or minus 2. In particular, what's going on here, if I were to graph this function, I get that. If you tell me the value of Bob is equal to 4, and I now want to know what is, for what value of x will give me that, what happens? Well, if I tell you that the height of this thing is 4, there's two places where the height is going to be the same. So I cannot tell you definitely what the value of x was, right? There's two different things that come out of this, and so this is not a function, right? Trying to go backwards here does not give me a unique value. It does not give me a function in terms of this process. Okay, so now the question is, what's the restriction that I need in order for this process of going backwards to be a function, right? We're looking for an inverse function. We don't want any ambiguity. And the problem here is that I can find at least one value for Bob, a valid value for Bob, where the output has, or I should say, where the input has two different values. Okay? And this is going to be this idea of something that's one-to-one. A one-to-one function is going to be a function such that for any given possible output, there's only one possible input that would have given me that particular value. Okay, so that's a mouthful. So let me restate that. Okay. So here's the statement. This is a definition. Oops, let me do this. Let me call it, give it a name. Okay, so I'm going to say a function is one-to-one. Don't do that. If I pick any A and B in the domain, A is not equal to B, then the value of the function can't be the same. This has to be true for everything possible. So what is this saying? This is saying, and if this is my function, and B, not quite so dramatic, okay, then there's no values of A and B where the outputs for f of a and f of b are the same. So in other words, I can't find a value f of b where this is going to be the same thing for another f of a. Okay? All right. Now, there's an equivalent definition. Okay? The equivalent definition, we will say if f of a equals f of b, then a equals b. Okay? So this is basically saying the same exact thing, but it's just starting with the height of the function rather than what's happening in the domain. Okay? So if I have something like this, this is not one-to-one, because I can find values of a and b. Right? I just have to find one. If I can find at least one values of a and b, so we'll call this a and this b, where the height, where a is not equal to b, but f of a is equal to b, f of b, this is violated. Okay? Notice this is also violated, because this says now, I know the heights of these two things are the same, but a is not equal to b, so that's not true either. Okay? So in this case, there's no place, no values of a and b that I can find where f of a is equal to f of b. Also, if I find the height of this function, there's no other place where that matches. So both of these things are true. Here, right, it's possible for me to find values of a and b where f of a equals f of b, but a is not equal to b. Okay? All right, so let's look at some examples. Before I do that, though, I just want to officially state this idea of an inverse function, because this definition of a one-to-one now gives me the ability to define when an inverse for a function. Okay? So what do we have? Suppose I've got a function that's one-to-one. And then g is going to be an inverse of this function if the following is true. F of g of x is equal to x for all x in the domain of g. And I also need this as well. Both of these have to be true. G of f of x equals x for all x in the domain of f. Okay? Both of those things are true. Life is good. So I'm going to look at